you find that the occupied photoemission spectrum will have a feature close to the Fermi energy and a very strong incoherent part. It will be in fact dominated by the incoherent part, the photoemission spectrum. Whereas the unoccupied part would be dominated by the coherent part, and there will be very small incoherent part. Look at also the energetics, because here the parameter strengths were chosen realistically from not to fit the spectrum but from other estimates. This one comes out at about 1.5 electron volt, exactly where you find the incoherent feature in experiment. And this is of course at the Fermi energy. This coherent feature appears at about 1 or 1.1 electron volt above the Fermi energy, in close agreement with what we find in strontium titanate, with oxygen vacancies or lanthanum. This incoherent feature you will not see in the unoccupied spectrum because the strontium features are very intense here and will completely swamp it. So the message here, in presence of disorder or inhomogeneity, the unoccupied part is dominated by the coherent peak and very weak incoherent peak, while the occupied part is dominated by incoherent peak, very weak coherent peak. And a very similar scenario appears even for the macroscopic inhomogeneity. And this is in perfect agreement with the experimental results, which would be otherwise virtually impossible to explain. In fact, no homogeneous model with any kind of self-energy correction, local or non-local, will be able to explain to you otherwise simultaneously the occupied, the unoccupied spectroscopy. Even if you try to generate a satellite in the occupied part from any homogeneous model, you'll have an intense satellite also in the unoccupied part. So no homogeneous model has a hope to solve or explain the experimental observation, and you have to take into account the disorder effects. So let me summarize this section of the talk. What I've shown you is that chemical substitution, and this is true for all compounds, substituted compounds that we study, that there is strong disorder. Disorder is introduced by the very fact that you are making substitution, chemical substitution. So it creates inhomogeneity. This inhomogeneity can be in different length scale. We have treated two extreme length scale, the microscopic length scale and the macroscopic length scales. In general, the results from such inhomogeneous system cannot be explained in terms of any homogeneous model, including the Hubbard model. And you have shown that if you take a Hubbard-like model and treat the diagonal energy as a random variable, then the experimental results, calculated results, which take into account the disorder effect, is in very good agreement with the experiment. With that, I conclude this part of the talk, and let me go on to the next. Yes, please.
How in Microsoft model, how do you deal with the disorder or database?
What happens basically, see, if you take the Hubbard model, homogeneous Hubbard model, okay? Think of the homogeneous Hubbard model in infinite dimension. That can be mapped onto an Anderson infinity model. Okay? Then all that it does is that you look at the transition metal ion, the one that you're interested in, and rest of the solid in a self-consistent way provides the bath into which the impurity is embedded, and the impurity is interacting with that. The Hubbard model in infinite dimension can be exactly mapped onto that. Okay? Now, that way, of course, when you use this is exact only in infinite dimension, and then you are applying it to three-dimensional problem. You know, 3 is very much lower than infinity. Okay, so then we call it a large D approximation. It is an approximation, but it seems to work extremely well in many cases. So that is for the homogeneous problem. Now for the disordered problem, now you can immediately see that if you have two different sites with two different kind of energies, each of them will decouple into two impurity models. Okay,